Okay, this video is covering the Z-transform and specifically the proof of the convolution result for the Z-transform. I think this is important to be able to do. It shows you how to manipulate summations in a logical, mathematical way. If you have plans on attending graduate school and taking courses in the areas of communication and signal processing, this is certainly the kind of thing that you need to be able to do. Okay, so let's get started. What we're going to do here is we're going to look at time domain convolution. So we know y of n is x of n convolved with h of n, gives us the output of a system with impulse response h of n. What we'd like to do is then find the z-transform of y of z. If it turns out to be the answer that we expect, it's x of z times h of z. Alright, so let's prove this. Okay, so to get started with a proof, you begin with the thing that you're looking for. Okay, so I want to know y of z. And that's going to be the sum from n equal minus infinity to infinity of y of n z to the minus n. Alright, so I then know what y of n is defined to be. Y of n is defined to be convolution. So I substitute convolution in for y. And then I know the definition of convolution. The definition of convolution is yet another sum. This time we have a dummy variable of summation, k equal minus infinity to infinity, x of k, h of n minus k. Alright, so this is the convolution. So this part expands into this green box. And then we still have the things on the outside that are left in the same form. Okay? From there, the next trick is always, or it seems like it's always, to interchange the order of summation. Okay, so instead of summing over the k variable first, sum over the n variable first. Okay, so we're going to switch the order of these. K equal minus infinity to infinity. Okay, then sum from n equal minus infinity to infinity. And then we just keep track of what has a k on it and what doesn't. Alright, so x of k has a k on it, so it's a constant with respect to the summation n. Okay, so x of k factors out and comes to the outside. Alright, so then we're left with things that depend on n, which would be h of n minus k and z to the minus n. Okay? Alright, from there we have to recognize that this is getting pretty close to the definition of a z-transform, but it's a little bit off. Okay? We notice this is h of n minus k instead of h of n. Okay? So, what I'm going to do here, you could appeal to the time shift property at this point, but what I'm going to do here is just do a change of variables. Let's make this h variable be some other letter m. Okay? So we're going to sum from k equal minus infinity to infinity. We're going to sum now over m. M equals, okay, now we have to, we're making this substitution. M equals n minus k. Alright, so as n goes from minus infinity, m would also be at minus infinity. Minus infinity minus k is still minus infinity. So the limits of the summation don't change. When n is positive infinity, m is also positive infinity. Okay, so You did things like that when you changed limits on integrals. Same thing happens with sums. Okay, so this would be h of m. And now, when I get to n, I can replace it. N is m plus k. Okay, so I'm going to have z to the minus m plus k. And I still have my x of k sitting out here. All right, so I just manipulated that sum a little bit with a change of variables. Okay. From there, what we notice is that this exponential will factor. Using properties of exponentials, I can bring the part that has a k on it outside this summation loop for m. All right, so this would be x of k, z to the minus k, and then I would have summation m equal minus infinity to infinity of h of m, z to the minus m. All right. And so what we notice here is that this is an inner loop. All right. This inner loop of the sum is the definition of the z transform of h. So I recognize that pattern. That's h of z. So from there, I would have sum of xk, z to the minus k times h of z. But this sum is also something you should recognize. That's the definition of the z transform of x. So this proves the result using just the definitions and interchanging the order of summation and going through the right math. We proved that y of z is x of z times h of z.